This chapter 19 is going to be based on energy and enthalpy, kind of like we looked at in chapter 5. We're just going to continue with that, but this first video is going to be based on sections 1 through 4, which is going to look at spontaneity of reactions as well as entropy, what that is, and how to calculate it. So the big question in this chapter is, how do we know whether a reaction will happen or not? We want to know in this chapter if a reaction is spontaneous. And we're going to talk a little bit more about spontaneous. But first, I want you to remember from chapter 5 when we talked about energy and enthalpy. Remember the first law of thermodynamics. The first law says that energy cannot be created nor destroyed. However, energy can be converted from, say, potential to kinetic, or it can be transferred from system to surroundings or from surroundings to system. Energy needs to stay constant, but it can be transferred. So even though energy can be transferred, we don't know if the process is favored to occur. And that's what we're going to focus on. So back to the spontaneous process. Something is spontaneous, like you probably know, if it proceeds on its own without any outside assistance. And we're going to look at some examples of spontaneous processes. A spontaneous process occurs in one direction only, and the reverse is always non-spontaneous. So a spontaneous process is always a one-way reaction. And when we're talking about something being spontaneous, it's definitely important to remember that spontaneous does not necessarily have to do with speed. So you could have a spontaneous reaction that is very, very slow. Think about an example of that. Rust, right? If iron rusts, that doesn't happen instantaneously. It happens over a long period of time, but that is a spontaneous process. That is what we're going to focus on in this chapter. So what you have here are a few pictures of spontaneous processes. All the way on the left, you have the nail rusting. That is spontaneous, but when you go the reverse, it's not. And in the middle, you have an example of two gases in container A and container B. If you open the valve in the center, the gas from container A will go over to container B to give equal pressures. And if you want to try to get all of the gas from B back into A, you would have to put energy in somehow. So that is not spontaneous. So notice one process is spontaneous. If you want to reverse it, it's not. And I think a great example is dropping an egg. Right? If you hold an egg up, you let go, it's going to fall, it's going to break. Well, if you try to go the opposite way, that's not spontaneous. And again, something that is important to remember, especially with the example of the rust, just because something is spontaneous does not necessarily mean that it will occur at an observable rate. Okay, that is kinetics. We've already looked at kinetics. That deals with rate. Spontaneous is just, will it occur on its own without any outside interference? So you could have something that's very fast. Okay, for example, dropping the egg. That's fast. You drop it, it breaks. But if you're looking at rust, okay, that happens over a long period of time. Thermodynamics tells us the extent and the direction of a reaction, but it does not tell us about the rate. And just one last thing about spontaneous versus non-spontaneous. A non-spontaneous process is not impossible. For example, if you try to extract iron metal from iron ore, okay, it's a non-spontaneous process. It doesn't happen if the iron ore is just left there, but that doesn't mean that it's impossible. You could make it spontaneous by changing conditions or by supplying energy. And so it's really important to remember, just because something is not spontaneous doesn't mean that it can't happen. And that's actually our focus for this thermodynamics chapter, is we're going to look at how can we change conditions to make a process or make a reaction spontaneous. So with our focus on thermodynamics, there are two driving forces for chemical reactions. One of them is enthalpy, which is your delta H. That's what we talked about earlier last semester when we looked at calorimetry. Okay, enthalpy is delta H. That is the heat absorbed by a system. Enthalpy, though, will not tell you if a reaction is spontaneous. It will only tell you if it's exothermic or endothermic. So again, enthalpy will not tell you if a reaction is spontaneous. Then the second driving force is entropy. That is delta S. We'll talk more about that in a second. Entropy is going to be a measure of randomness. And in nature, okay, so if you're just sitting in a classroom, okay, in nature, reactions move toward lowest energy and highest entropy. An example that I like to use is most kids want to be lazy. And what that means is when they are lazy, their room gets really messy, right? So very low energy, you're being lazy, high entropy. Your room gets messy. It gets more random and more disordered. That's what happens in nature. Enthalpy cannot always tell us if something is spontaneous because, for example, most exothermic reactions are spontaneous, but a very common example is ice melting. Okay, when ice melts, it absorbs energy. So that's actually an endothermic reaction that is spontaneous. So you cannot rely on delta H to tell you. So what we look at, and this is going to be a major focus of this chapter, what we look at is entropy. So entropy is a state function that we talked about before. It is a thermodynamic state function represented by S. Okay, so S is the variable for entropy. I mentioned that it is a state function. What that means is it depends only on the present state of the system, not the path it took to get from initial to final. So it's a state function. It only depends on S final and S initial. That's all we care about. But entropy is a measure of how energy is distributed in a system. Okay, so what that means is it is a measure of randomness. Okay, so out of all of that, the biggest thing, entropy is a measure of randomness or a dispersal of matter. Entropies are usually positive for elements and compounds. So usually delta S is positive for elements and compounds. And then you also have the units for entropy. But with entropy, like I said, you want to think about it in terms of randomness or disorder. When particles are more free to move, they spread out more and matter is dispersed more, okay, it becomes more random, and that is an increase in entropy. Or if you create more particles. So say you start with 2 molecules of gas and then you end up with 4. It becomes more random. You have more particles moving around. That means it's more random. That is an increase in entropy. So like I said before, entropy is a state function. So it only depends on the final and the initial. So with that, we can look at the change in entropy. We can look at delta S. So to find delta S, which is the change in, you just take final minus initial. If your delta S is greater than 0, if it is positive, then you have an increase in entropy and you have greater disorder. So again, delta S is positive, you have greater disorder. If delta S is negative, you have greater order. When delta S is positive, that is when it is spontaneous. Okay? Delta S being positive means it's more disordered, it's more spontaneous. If delta S is negative and you have more order, that is not spontaneous. So the second law of thermodynamics deals with entropy. In any spontaneous process, the entropy always increases. So the entropy of the universe always increases if it is spontaneous, okay? Because the universe wants maximum disorder. The universe wants chaos, right? So if it's spontaneous, delta S of the universe is greater than 0. This is super important. Okay, a process that involves an increase in order. So if entropy is negative, it can be spontaneous if it causes a greater change in entropy in the surroundings. So that's where it gets kind of weird. We're going to focus more on that later when we talk about Gibbs free energy. But the biggest thing is that the entropy of the universe always increases if it's a spontaneous process. So like I mentioned, entropy is not conserved. The universe seeks maximum disorder. It wants as much chaos as possible. Delta S should be positive whenever you're talking about entropy of the universe. So with entropy, very much like enthalpy, the standard entropies, which is represented as S naught, have been determined for substances, and these values are based on the third law of thermodynamics. So we've already looked at the first law and the second law. The third law of thermodynamics says that the entropy of a pure crystalline substance at 0 Kelvin is 0. So I want you to think about how this happens. Entropy is a measure of disorder. So disorder is based on randomness. Well, if the temperature is decreased, what happens to the motion of particles? It also decreases. If the motion of particles decreases, the energy decreases. When the energy decreases, entropy then also decreases, because as energy decreases, your particles slow down. When your particles slow down, they become more orderly, right? It's not as chaotic. So if we lower the temperature all the way to absolute 0, what happens to motion? All motion stops. So when all motion stops, there's no energy, right? And the individual atoms are completely still. So they're in a crystal lattice, they're perfectly ordered, they're not moving. That means there is no randomness at all. There is no disorder. So your entropy is 0. So that's actually how they came up with this third law of thermodynamics, because at 0 Kelvin, there's no motion, so there's no disorder, no randomness. So that's why it is 0. Okay, so here's some qualitative rules about entropy. Entropy increases as you go from solid to liquid or from liquid to gas. Because your particles, think about the particle diagrams that we've looked at. Your particles start really close together in a solid. They're not really moving, they're just kind of vibrating. And then going to a liquid or a gas, they move faster, they start to bump into each other, they become more disorderly, more chaotic. So your entropy increases. Your entropy also increases as your number of moles of gas increases for the same reason. The entropy of any material, any molecule increases with increasing temperature. Okay? Again, think about the particle diagrams. It also increases if you dissolve a solid or a liquid into a solvent. Okay? Because think about salt in water. You're putting a solid into water and it's dissociating into its ions. It's becoming more disorderly. Entropy is higher for weakly bonded compounds than for compounds with very strong covalent bonds. Again, similarly, think about if it's weakly bonded, those bonds are easier to break. It becomes more disorderly. Entropy increases as your particles increase. It increases as electrons increase, and entropy increases as your mass, number of atoms, number of heavier atoms, or thing like that increases. Okay, so you have a lot of ways that entropy can increase. Again, I can't stress enough, think about it in terms of particle diagrams that we've looked at. Think back to the kinetic molecular theory with gases. Right? Entropy is all about how disordered something is. So looking at this graph, you can see that entropy changes dramatically at a phase change. We can look here, your entropy starts to increase slightly, and then when you hit that phase change, it jumps dramatically. So the reason why is because entropy increases with the freedom of the motions of molecules, right? So as your molecules can move more, they become more disordered, and entropy increases. Okay, so like we talked about before. This slide gives a great example with these particle diagrams, right? So ice is much more orderly. Liquid water, they're still somewhat orderly, but they are still moving. And then vapor, it's when it becomes the most chaotic or most disordered. So we've been talking about these laws of thermodynamics, and I just wanted to give you a slide that contains a summary of the three. The first law, what we looked at before, is that energy is conserved in any process, so energy is neither created nor destroyed. The second law deals with entropy of the universe. So in any spontaneous process, the entropy of the universe increases. So this is your delta S of the universe is greater than 0. And then the third law is that when you are at 0 Kelvin, you're at absolute 0, and the entropy is also 0.